Hi everyone. So here's the examples for today, so you can follow along with this video. Righto. So the first one here is this Botanic Gardens one from last time. So if you haven't tried this this example yet, you might like to try it first, and then pause the video and try it first, and then come back and check the answers afterwards. Okay, so I'll have a go at it now. So the first question is, would it be possible to walk the gardens starting and finishing at the main gates and travelling on every path? Well, of course, this is an Eulerian circuit. I'll just say EC for Eulerian circuit. And this is not possible. No. The reason is, for an Eulerian circuit, all vertices must be of even degree. Now we can see here that B and E are of odd degree. So as B and E are of odd degree, this type of circuit is not possible. So add an extra path so that such a circuit is possible. Okay, well, we want B and E to be of even degree. So if we put a path or an edge between those two, now they're of even degree, and so are all the other vertices. So we can have an Eulerian circuit. There's probably various circuits that would be possible, but I'll try this one. Let's do this. A to B to E to B to F, and so forth, D to D to F to C to A. So remember, with an Eulerian circuit, we want to be able to draw the circuit without lifting our pen from the page. That's the way you can tell if it's a circuit or not. So whether it's Eulerian circuit. So A to B to E, back to B to F to E, to D to F to C to A. There's our circuit. Righto. Now, from here we're going to start talking Hamiltonian circuits and paths. So if you want to pause the video and read through them before I talk about them, you can. Okay, so Hamiltonian circuits and paths are different from Eulerian circuits and paths because we're visiting every vertex rather than every edge. So remember, E for Euler and E for edge. Alright, so we're visiting each edge. E for edge is in an Eulerian circuit. In a Hamiltonian circuit, well, we're going to each vertex. Okay, so if you want to try finding Hamiltonian circuits and paths in this network here, go ahead and pause the video, then I'll show you some that I found. Okay, so a circuit for this one, A to B, C, E, D, back to A. So that looks like this. A to B to C to E to D to A. So we didn't go on every edge, but we went to every vertex. That's a Hamiltonian circuit. Hamiltonian path, well, I did this one. A to B to E to D to C. So we've gone to every vertex here, pretty much the same, except I just stop at D. I don't end up back at A. So not every edge being covered. Okay, so you guys go ahead and find the things for this one. Hamiltonian circuit starting and finishing at A. Alright, if you want to try all these, go ahead, pause the video, then I'll do it. Okay, here's my Hamiltonian circuit. A, B, C, D, E, F, G. So A to B to C to D to E to F to G, back to A. Oh, don't forget, put that A back on the end there to show I've gone back to A. So just really round the edge, or sorry, not round the edge, round the outside of the network. An Eulerian circuit starting at A. Is that possible? No, not possible, because D and E are of odd degree. An Eulerian path is possible though, because we have two odd vertices. And when we find an Eulerian path, we need to start and finish on one of the odd vertices. Doesn't matter which one, but you've got to start at an odd vertex. So for this one, I tried this. I started at E, beg your pardon, E to F to G to A, E, D, A, B, C, D. Let's try this one. E to F to G to A to E to D to A to B to C to D. So I covered every edge and ended up somewhere else other than where I started. Okay, I'll get rid of all that stuff now, and let's do this Hamiltonian path from E to B. I did this. B, F, G, A, D, C, B. Hamiltonian path. E to B, okay. E to F, to G, to A, to D, to C, to B. Okay, very nice. Didn't cover every edge, but we went to each vertex. If we're going from G to B, I did this. G, F, E, A, D, C, B. G, F, E, A, D, C, B. And surely there are other ways of doing these, but that's the one that I picked. Okay, so explain the difference between a Hamiltonian circuit and an Eulerian circuit. Well, this one visits every vertex, whereas E for Euler, E for edge, visits or covers rather every edge. All right. So you guys might want to think about these, then have a go at these. So pause the video. Okay, so here are my answers to these ones. I think this is an Eulerian circuit. This is a Hamiltonian circuit. This one's an Eulerian path. This is a Hamiltonian circuit, and finally a Hamiltonian path. Okay, so you can debate those with me when I get back. Okay, here's the stuff on travelling salesman. Shortest path analysis. What's interesting about this is there's no known method to solve these. It's all really just down to trial and error or algorithmic approaches. So it's a big thing in maths, people trying to find a way to solve this problem, but really it just comes down to trial and error in a way. Go ahead and find 3 different ways that this would work. Firstly, the travelling salesman needs to visit each vertex and then head home. So we're talking about a Hamiltonian circuit here, Hamiltonian circuit, HC. So a path, well actually it's not a path at all, it's a circuit. What type? A Hamiltonian circuit. Because he needs to visit each town which are vertices and get back to where he started, which is a circuit. So find 3 routes through this and see which one is the shortest. Then I'll have a go at it. Okay, I'm going to try it now. All right, I'm going to call this route number 1. This can be 2 and this can be 3. All right, so route 1, I'm going to go this way. Go down here from home to town D, then across to B, down to C, and then home again, like that. Okay, so route 1 is a distance of 12 plus 13 plus 7 plus 8. which gives a total of 40. Not sure what the units are here. I don't think he'd walk 40 kilometres with the salesman. Not sure. Okay, number 2. Just going to go this way. Okay, so the distance for that walk is 10 plus 7 plus 10 plus 12, which gives a distance of 39. Okay, and find a different way for number 3. Might do, which way will I go? Maybe go like this, up that way, across, down through there. Okay, so route 3, we're going 10 plus 8 plus 13 plus 10.
Why is this so?
I'm just doing a recording here. Yeah. So
Am I interrupting?
Oh, it's all right. No, don't worry. What do you need? Okay, just someone had to ask me something there. Sorry about that. Okay, so this route adds up to, what have we got? 18, 28, 31. Is that 41, I think? So the shortest that I can see is route 2. You guys might find a shorter one if you look around, but I think that's the shortest, isn't it? 39 whatever kilometres or something, who knows. All right, so trial and error method there. Now if we look ahead at this next one, trial and error method here, basically just find a few different paths through the network. Let's see if we go right through the middle, up through that way. 3 plus 8 plus 15 plus 5 gives us, what is that? 11, 21, 26, 31. If we were to go around the outside here, 20 and 8, 28 plus 5 gives 33, so that's not as short. We could go through this way. Three and 10, 8 make 11, 10 makes 21, 29, 34, that's longer. Or we could go through this way. 3 and 8 make 11, and 7 makes 18, and 11 makes 29, that's 34 as well. So that red path, the first one I did, is the shortest. So a little bit arduous, this method, the trial and error. We can take an algorithmic approach as well. So I'll show you that, then you guys can start doing some questions. Okay, so trial and error method for this one here. Well, if we muck around with this a bit, you guys give it a go and see what you can find as the shortest distance. Then I'll show you. So pause the video and play with that until you get the shortest distance. Okay, so if you use the trial and error method on this one, you should get this path as the shortest one. Okay, which is P to R to U to V to X, and that adds up to 140 minutes between the towns there. Okay, so let's demonstrate this with the algorithmic approach, which you may be required to do. So here we are starting at P with the 0. Now to get to Q, the shortest way is 30, and we keep a note of where we came from. We came from vertex P. So 30 via P, that means. Now from P to R, 60 via P, and from P to S, 90 via P. Okay, so just going in those directions there. Okay, now, what's the shortest way to T? Okay, we could do 30 and 40, making 70 via Q. Or we could go from R, 60 and 20 makes 80 via R, that's longer, isn't it? So we wouldn't count that one. We keep this one. That's the shortest way to T. So you keep doing that and eliminating the longer route. Okay, let's try it again on U. 90 via R. Now there's no other real way to get to U, so that would stay. We wouldn't test any others. But V, alright, we could come 80 via R, or 110 via, sorry, 80 via U, 110 via R, or 130 via P, or via S. So obviously those two are longer. 80 via U is the short way. Okay, for W, I'll just neaten this up a little bit. So 80 via U is the short way there. Okay, for W, we could come 120 via T, but this way shorter, isn't it? 90 and 15 make 105 via U. So scrub him out. This is the shorter way. Okay, finally to X, there are three different options. 155 via W, 160 via U, so 90 and 70. I'm not even going to bother writing that down because it's longer. Or 80 and 40 via U. Now what have I done there? That doesn't add up, right? 60, 90, 100. I haven't done that bit right, have I? Beg your pardon. Sorry, that should have been 100. There, sorry about that. 100 there. Yep, I was a bit worried because it wasn't going to be 140 otherwise. 140 via V. So we'll scrub that out. That's definitely the shortest way. We see that 140, which matches up here. Sorry about that mistake. Hopefully you could pick that what was happening there. So that would be along this path here. So we know that we've come from V, beg your pardon, not along that path. I'm not doing very well on this one, am I? This path here. So we know that because we've come from V back to here, V, and then that one was from U. So back to U, back to R, and back to P. So if you keep a track of which vertex you came from, the shortest way, then you can backtrack that using the algorithmic approach. So practice both methods and be able to use both methods, the trial and error or the algorithmic approach. Okay, so I'll set some questions for the relief teacher to show you guys, and you can use this video, go back and look at all the different examples that have been done, and that should help you to do those questions today. All right, thanks a lot. I'll see you guys soon.